In this video, we're going to look at mastering the DAC output. This is a digital to analog converter. That's pin 0 here. The very first thing that we're going to do in the void setup is set the resolution of the DAC. We don't need the beginning piece over here. We can get rid of it. If you forget some of the commands of how to set things up, you can always go under Help to Reference, and that will bring up the reference page. And if you scroll down here, you will see that we have a couple of options here for resolution. The Duo and the Zero, they use the SAMD21, which is the same microcontroller that we're using. And you can see that we have a command to set the resolution for analog write and analog read. The DAC is the analog write. That's going to be the outputting the analog voltage. And so we're going to use this command here. And if you open up and see the details, it says, okay, it's just a way of setting the resolution in terms of the number of bits. The DAC in the Xiao is only a 10-bit DAC. And so we're going to use 10 as the variable that'll go inside the parentheses. So this is literally the command that we're going to use. We're going to copy that, and then in our code and in the sketch, we're going to put that in the void setup. So do the resolution, and we're going to make it 10 bits. And that just sets up the default case. And then literally in this exercise, all we're going to do is write a value and then read the value. And that with 10 bits, that's a total of 1024 different levels, starting at 0 to 1023. Here's what we're going to do. Initially, we're just going to type in the bit level. And we call these units the bit level from 0 to 1023 in the case of 10-bit resolution. We call each of the levels analog to digital units, ADUs. And so when we type the value in, it's going to be an integer 0 to 1023, and that's going to correspond to the output levels of roughly about 0 to the voltage rail, which is roughly 3.3, but we measured as 3.28 volts. So let's do that. We're just going to toggle a value in and turn it on and turn it off. And so it's literally going to be an analog write. The pin number is 0, and we're going to first put in 0, and that will start us out at 0. And then we're going to go analog write, be pin 0, and let's put in 1000. So close to the limit, but not the very top. We'll explore those limits in a minute. And that's it. And we're just going to repeat that. And what do we expect to see? We're going to see the output toggling at the fastest rate that it can toggle, and we're going to measure that with the scope. And that will give us an idea of the on time and the off time. Now, when we run this code, the first thing it's going to do is ask us to save it, because I set up, hey, save it before you run it. And so, it'll save it in wherever we tell it to. Here's my sketches here. My general labeling scheme for sketches I write, as opposed to ones that I get elsewhere, I like to put my initials in the beginning of it. And then this is going to be something about what this is doing. This is going to be the Xiao, and this is the DAC, and I'll put a date code so that I can identify when it was created. And we're done. Okay, now it's going to upload. Let's compile, compile. Now we want to make sure that, in order to do that, we have selected the correct board, which is the SAMD21, the Xiao, and we want to make sure that we have the correct board COM port, and there it is, COM7, and all that is correct. And so we uploaded it, and hey, we're done. And so we ought to see on the output, we ought to see the analog voltage going roughly 0 to 3 volts. Let's take a look at that. So first of all, I'm going to turn on the scope, and here is what is on the scope screen. I got my 10x probe, and of course here's the analog output. This is ground, so we're going to stick the ground spring tip in ground, and we're going to stick the other end in the signal. There we see it, but of course, it's going really fast, so I'm going to expand the time base Wow, there we go. And now we can literally read off the front screen how long the execution time is. And so, we're starting over here. Let's see. So it goes from the center over here. It's about 3 volts coming out. It's a little bit more than that. 0 volts to 3 volts. That's great. And let's see. And so it's going to go from, here's 1 division to about 2.5 divisions is the execution time. And so that is about 5 microseconds to go on and off. And we see the on time, we see the ramp up for it as well. So it's about 5 microseconds, which is about 200 kilohertz, is the toggle rate going on and off. Now you see the little ghosting images here. That's because of the timing that's involved here. That the Xiao module is constantly checking for interrupts. We can turn them off locally as needed, but if we turn them off and we leave the program in the program while they're off, that will brick the module, and I'll demonstrate that in one of the next videos. But for now, just ignore that ghosting. That just says that, okay, we're not getting perfectly reproducible timing. We'll have to control timing within a loop if we are concerned about accurate timing. If you've gotten this far, you have now gotten your analog to digital converter working. We can change the value a little bit. Let's see. So right now the value is 1,000. If we make it 100, we ought to get a smaller voltage. Let's upload and check that. And there we go. There's our smaller voltage. Still looking pretty good. Get the trigger going there to get and beautiful looking signal. Okay, so for now, one of the first questions we want to ask is how accurate is the analog output? And so to do that, we're going to write a little bit of code here in order to make it easier to assign a voltage and then have that voltage as the output. And to do that, we're going to need some more variables. And so I'm going to put some variables in the beginning. Always put the variables at the top here. I'm going to do something really simple. I'm going to define a voltage that I want the DAC output to be. And I'm going to call that, I'm going to use a float for that. And that's going to be a voltage for the DAC. DAC is always an output anyway. And I want the units for this. I'm going to have 2 units. I'm going to have voltage. That's why it's a float. And I'm going to assign that as, suppose I want 2 volts, 2.0. I need to convert that into ADUs. And here's how we're going to do that. So I'm going to use a long, I'm going to use the same variable, DAC, but this is going to be in units of ADUs, analog to digital units. This is going to be the integer. And that's going to equal the voltage of the DAC that I want to have coming out in volts. That's the value I want. And I have to scale that. I have to divide that by, remember our full scale is 0 to 1023. And so I need to, and it's supposed to be 0 to 3.3 volts is mapped into 0 to 1023. And so I want to divide this by the maximum voltage. And instead of just hard coding in 3.3, I'm going to give ourselves a little bit better accuracy, and I'm going to create a new variable. And this is going to be a voltage that is the DAC reference, and it's going to be in units of voltage. And now I've got a number. This is the fraction of the voltage I want compared to the maximum voltage, and that's going to be scaled by 1023. Okay, and now I need to add a new variable here, and this is going to be, again, it's a voltage, so it's a float, V, the DAC, and this is the reference in V. You notice the style I use to label I have the first letter tells me what it is, what kind of quantity it is. I have a descriptor about where it's from or something about it, and then the last little bit here are the units. So it's a voltage, it's related to the DAC, it's the reference voltage in units of volts. And now remember that value that we measured, 2.80 volts, that's going to be the reference voltage. And when I calculate this, this is now the value in ADU. And so I'm going to come over here, and the voltage output, I'm going to output the DC value, and the voltage value and output is the voltage of the DAC in ADU. Now, generally, if I have an integer, to keep track of the fact it's an integer, the fact that it's in units of ADU means it's an integer. Otherwise, I'd put a little I in front to remind myself, oh yeah, that's an integer. But the fact that it's in units of ADU is good enough. And so that's what we're going to output, and that's it. That's the entire loop. I'll clean this up a little bit, and that's it. So let's try it again. Now when I upload, because I have that flag set in preferences, this will also save the application. Now what I expect to see is an output that is 2 volts. And so we're going to look at that with the scope, and we're going to look at that with the digital multimeter. So we uploaded, and let's adjust the scale. And there we go. Now, I expected 2 volts. I'm getting 2.3 volts. And perfect example of how come. Well, that's because now I see, oh, I forgot the reference value. The reference isn't 2.81, it's 3.28. That was actually the reference voltage. It's not what I expected to see, so there's a reason for it, and oh, I typed in the wrong number. Let's try it again. So we'll upload that code. We'll compile. We'll upload, and let's see what the voltage is we have coming out. Oh, now it's closer to what I expect. It's about 2 volts, 1.99 on the scope. Now let's use our digital multimeter to see what that is. So, it's our digital multimeter. We'll clear the screen a little bit. Here's the voltage, and now that's looking at the output of the 3.3 volt rail, and now let's look at the output of the DAC. We expect about 2 volts, and we're getting 1.98. So we are within, I have to be careful because I don't want to short out the DAC. There we go. We're at 1.99. So we are 10 millivolts off from 2 volts. That is 0.5%. Without doing anything except using that reference voltage, we are within 0.5% of the target value that we're looking for. And we could do a little experiment. Suppose that we had said naively, oh yeah, the output voltage is actually 3.3. So let's make this 3.3. Now let's run the code again, and we'll see what the voltage coming out is, because we're going to change the ADC value, and we'll see what the output does. And here we go. And now we're off by about 1%. We're 20 millivolts off from what we want to have, 2 volts, and that's because of it's still 20 millivolts out of 2 volts, still 1%. So without doing anything special, just naively using that 3.3 volts as our reference, we can get within 1% absolute accuracy, which is great. And if we want to improve that, we measure the 3.3 volt rail as we did and use the actual value for it of 2.28. So let's go back and do that. 2.28. And now that will give us a little bit better accuracy in the output. Still a little bit better than 1%. And that is as good as can be expected for this ADC. The fact we don't have a reference voltage to use says, hey, there's a fundamental limit to the absolute accuracy. Now, the one last piece of information we'd like to get is, hey, what's the output resistance, the Thevenin resistance of the DAC channel? Now, generally, the DAC channel is not going to be able to drive a lot of current. The spec is typically about 7 milliamps max current. And so if I put my 100 ohms here, I'd get 30 milliamps of current. This poor DAC is not going to be able to drive that. Let's try the 100 ohms. Okay, so here's our 100 ohm resistor. The loaded is 1.58. That difference is 0.41 volts. And so what's the Thevenin resistance? That's going to be equal to the resistor we're adding, which is the 100 ohm resistor, times the delta V over the voltage that is loaded. And that is 100 times 0.41 divided by 1.58. And to get a little bit more accurate value, and we can just kind of estimate this, do it in our head. Here's one, and this will go in here about 4 times. This is about a quarter, which is about 0.25 times 100, which is about 25 ohms. So the output resistance, Thevenin resistance of the DAC, is about 25 ohms. You know what? That's pretty darn good for the DAC. However, we don't want to use the DAC to drive very much current. What's the current that we've got now? The current that we're driving is going to be the voltage, which is 1.58 volts, divided by 100 ohms. It's about 16 milliamps. And notice, the voltage has dropped down. And so we want to keep, if we want to maintain the accurate value of the voltage out, so we don't have much voltage drop across the internal Thevenin resistance, we want to keep this current in the milliamp kind of range, which means if we need more than a few milliamps of current, don't drive the device with the DAC directly. We want to use a buffer. And we're going to show you an example of using a high current op amp as a buffer for the output of the DAC. Okay, so we've got it all set up. We can measure the voltage coming out. We got it calibrated. We know the output resistance of the DAC. We know pretty much everything we need to know about the DAC. We know how to write code to it, and we saw the turn-on time for it. We got about a 200 kilohertz period for it, and it took a fraction of a microsecond for it to turn on. So now we know most of what we need to know about the DAC, and we can take a look at the ADC.